Across Canada, smoke from hundreds of wildfires has traveled thousands of miles, choking the skies over Toronto, Boston, New York, and communities across the Great Lakes, Midwest, and Northeast. Major cities have spent days under thick haze and dangerous air quality alerts, with more than 100 million people affected during some periods. Current reporting has confirmed that smoke from more than 800 Canadian fires moved deep into the United States, creating unhealthy conditions across a broad part of the continent. And according to the agencies tracking Canada's fire season, the worst may not be over. Officials warn that wildfire danger could continue increasing through the hottest and driest part of summer, even though the season began more quietly than the previous 2 years. This is what is happening across Canada, why the situation changed so quickly, and why government forecasters say the risk may remain elevated for weeks. Canada's 2026 wildfire season began deceptively slowly. By early June, officials had recorded just under 1,700 fires, with approximately 166,000 hectares burned nationwide. Compared with 2023 and 2025, both of which ranked among the worst fire seasons in Canadian history, those early numbers looked almost reassuring. But that apparent calm did not last. By mid-July, the picture had changed dramatically. Government tracking showed more than 3,000 fires during the season, with a total burned area larger than Jamaica. More than 800 fires were active across British Columbia, Alberta, Saskatchewan, Manitoba, Ontario, Quebec, New Brunswick, Nova Scotia, and the Northwest Territories. At least one firefighter died while battling a blaze in Nova Scotia's Annapolis County, while officials confirmed destroyed structures and evacuations in several provinces. The important point is that wildfire danger in Canada does not always appear all at once. It builds gradually as heat dries vegetation, soil moisture falls, and weather patterns create more opportunities for fires to spread. A slow start does not guarantee a quiet summer. In fact, federal officials have warned that the risk can increase sharply later in the season, particularly when high temperatures persist through July and August. Canada's Federal Wildfire Outlook released in July warned that fire danger would continue rising as the summer progressed, even though total activity at that point remained below the 5-year average. Environment and Climate Change Canada forecast above. Average temperatures across much of the country, combined with dry conditions in regions including Manitoba and northwestern Ontario. Fire danger models identified the Northwest Territories, Nunavut, northern Manitoba, and areas surrounding Hudson Bay as especially vulnerable. Elevated risk was also expected to extend into northern Ontario and Quebec. These regions contain vast forests and remote communities, which can make fires difficult to detect, reach, and contain once they begin spreading rapidly. The reason the risk increases over time is straightforward. Every hot, dry day removes more moisture from vegetation. Grasses, shrubs, fallen branches, and forest floors become easier to ignite. When strong winds arrive, an existing fire can expand quickly, throw embers ahead of the main front, and create new fires far beyond the original burn area. That combination of heat, dryness, and wind has already sent Canadian wildfire smoke far beyond the regions where the fires are burning. In mid-July, fires across northern Minnesota and western Ontario produced thick plumes that were carried southeast by prevailing winds. The smoke spread across the eastern half of North America, affecting cities including Toronto, Boston, New York, Chicago, Detroit, Minneapolis, Washington, and communities throughout New England. The pollution was not simply visible as haze. Fine particles in wildfire smoke can penetrate deep into the lungs and worsen asthma, heart disease, and other respiratory conditions. Health agencies in both Canada and the United States issued air quality alerts over a wide area, advising vulnerable residents to reduce prolonged outdoor activity and remain indoors when smoke levels became unhealthy. Recent reporting documented dangerous smoke across the Midwest and Northeast, with air quality warnings affecting millions of people and some cities recording hazardous conditions. This pattern has become increasingly familiar during major Canadian fire seasons, but familiarity does not make it less serious. Smoke can travel far beyond the fire zone, turning a regional disaster into a continental public health emergency, and the conditions driving that spread are not isolated. Heat waves, drought, strong winds, and extremely dry forest fuels are interacting across large parts of Canada. As long as hot, dry weather continues, officials say the wildfire threat will remain elevated. To understand why they are taking that warning seriously, it helps to compare this year with the recent history of Canada's most destructive fire seasons. Canada's 2023 wildfire season remains the worst on record, with more than 15 million hectares burned nationwide, an area roughly comparable to the size of Nepal. The 2025 season ranked as the second worst in the country's history. Those two seasons changed how officials, meteorologists, and the public view Canadian wildfires. They are no longer treated only as regional emergencies that affect isolated forests for a few weeks. They are increasingly understood as continental scale events capable of degrading air quality across much of North America for weeks or even months. The current season remains below the 5-year average and well behind the pace of the catastrophic 2023 fires. But officials have been careful not to describe that as a guarantee of safety. The underlying conditions that contributed to recent extreme seasons are still present in many regions. Prolonged drought, warmer than normal temperatures, dry ground vegetation, and large amount of available fuel. That is why federal agencies continue urging residents to follow official monitoring systems such as the Canadian Wildland Fire Information System. A relatively calm beginning can change quickly if a heat wave arrives after weeks of drying. A fire season is not judged only by how many fires are burning at one moment. The timing, size, speed, location, and weather surrounding those fires can alter the overall danger dramatically. The United States is facing a serious fire season at the same time. American officials have recorded close to 40,000 wildfires in 2026, burning more than 3.6 million acres, including roughly 500,000 acres in only the previous 2 weeks. According to the National Interagency Fire Center, that represented nearly 10,000 more fires and almost 1 million more acres burned than the 10-year average by mid-July. Colorado and Utah were among the hardest hit states in the American West, and 3 firefighters died near the end of June while battling fires along the shared border of those states. The fact that severe fire activity was accelerating on both sides of the Canada-U.S. border led climate researchers and emergency officials to describe the summer as part of a broader pattern of climate extremes rather than one isolated regional crisis. So what happens next? Canadian forecasters have identified August as a period when fire danger could remain high or increase further. Above average temperatures are expected to continue in several areas, while dry conditions may persist. British Columbia, Alberta, and the Northwest Territories have been named among the regions facing some of the highest ongoing risks, although local conditions can change from week to week. Wind shifts, isolated rainfall, thunderstorms, and changes in humidity can all influence the situation. A province may see improving conditions in one area, while a nearby region experiences a rapid escalation. That is why officials avoid relying on one national number and instead track fire danger at local and regional scales. For communities across Canada, and for people in the northern United States who regularly experience drifting smoke, the guidance remains consistent. Follow official fire maps and evacuation notices, check air quality alerts before exercising outdoors. Reduce strenuous activity when smoke levels become unhealthy. People with asthma, heart conditions, older adults, children, and anyone with respiratory vulnerability should take particular care during severe smoke events. Anyone living near an active fire should also maintain an emergency plan. Conditions can change with little warning if wind direction shifts or a fire crosses containment lines. Residents may have only a short time to leave, especially in remote areas where roads are limited, and emergency crews must cover large distances. Understanding how officials classify fires is also important. A wildfire is generally considered out of control when crews determine that suppression efforts are not containing its spread. In other words, the fire is continuing to grow beyond established control lines despite active firefighting operations. When the number of out-of-control fires increases, provincial resources can quickly become insufficient. Provinces may then request federal assistance, additional aircraft, specialized crews, equipment, or logistical support. Organizations such as Team Rubicon, a veteran-led disaster response group, have also become increasingly visible in Canada's wildfire response, supplementing government teams during periods of widespread activity. Another important distinction involves fire count and burned area. Those two measurements can tell very different stories. One year may produce many small fires that crews contain quickly. Another may have fewer fires overall, but several enormous blazes that burn through hundreds of thousands of hectares. Officials have noted that, compared with the same point last year, Canada has seen periods when the number of fires was lower while the total area burned was much larger. That means raw fire counts cannot fully describe the severity of a season. A smaller number of fast, moving fires can cause more destruction than hundreds of smaller incidents. This is why agencies track multiple indicators at once: total fires, active fires, out-of-control fires, hectares burned, fire intensity, evacuations, destroyed structures, firefighter safety, and smoke movement. Together, those measurements reveal the true scale of the crisis. But the deeper question is why Canadian fire seasons have become so volatile in the first place. Wildfires need three basic conditions to spread rapidly: dry fuel, warm temperatures, and a source of ignition or strong winds that can push an existing fire into new territory. In recent years, Canada has experienced all three across increasingly large areas at the same time. Warmer winters have reduced snowpack in many regions. When less snow accumulates, less water is available to soak into the ground during spring melt. Soil and vegetation begin the warm season drier than they would have in the past. If rainfall remains limited, that moisture deficit continues to grow. Extended drought has been especially important in parts of the eastern Northwest Territories and Atlantic Canada this year. Dry vegetation becomes highly flammable, and the fire season can begin earlier than normal. When summer heat waves arrive, the already dry landscape can move into extreme fire weather conditions for longer stretches. High temperatures do more than make the air uncomfortable. They increase evaporation, draw moisture from plants, dry the soil, and reduce the amount of water available to slow a fire. Heat can also create unstable conditions that help fires generate their own weather, including strong updrafts and shifting winds. In the most intense cases, a fire can produce towering smoke columns and spread in directions that are difficult for crews to predict. Wind adds another layer of danger. It can carry embers across roads, rivers, and fire breaks, starting new fires ahead of the main front. Strong winds can also push flames through forests at extraordinary speed, leaving crews little time to establish containment lines. When heat, drought, and wind overlap, a fire can grow much faster than emergency agencies can respond. This is one reason modern wildfire seasons are being treated as recurring, large-scale threats rather than short, isolated emergencies. 3 of Canada's 4 most recent seasons, including 2023, 2025, and potentially 2026, have been described as significantly worse than historical norms in at least some regions. Each season has followed its own pattern, but the repetition itself is becoming difficult to ignore. One year may begin with early fires in the west, another may see the greatest danger in the north or east. A season can start slowly and then accelerate during a persistent heat wave. The location changes, but the larger ingredients remain similar. warmer conditions, drier vegetation, and weather capable of turning small ignitions into large, fast-moving fires. That repetition is why climate researchers and emergency planners are focusing not only on responding to individual fires, but also on preparing for a future in which extreme seasons become more common. Communities are increasingly treating wildfire preparedness as a year-round responsibility. In British Columbia, Alberta, and other high-risk provinces, residents are developing evacuation plans, creating defensible space around homes, securing roofs and vents, and monitoring fire danger ratings. Defensible space does not guarantee a property will survive, but reducing nearby combustible vegetation can lower the chances of flames and embers reaching a structure. Emergency planning is especially important in rural and remote communities. A single road may serve as the only evacuation route. Smoke can reduce visibility, close highways, and create dangerous driving conditions. If multiple communities require evacuation at the same time, local authorities may face difficult decisions about transportation, shelters, fuel, and medical support. Smoke creates problems even for people far from the flames. Fine particulate matter can remain suspended in the atmosphere and travel hundreds or thousands of miles. Wind patterns can move smoke from Ontario or Manitoba into the United States, where it may settle over major urban areas. Temperature inversions can trap pollution near the ground, making air quality worse even when a fire is not nearby. Recent smoke events demonstrate how quickly this can happen. In July, smoke from Canadian wildfires affected large parts of the United States, prompting air quality alerts from the Midwest to the Northeast and Mid-Atlantic. Reports described dangerous conditions in cities including Chicago, Detroit, Minneapolis, Toronto, New York, and Washington. Public health response depends on the concentration of fine particles, the duration of exposure, and the vulnerability of the population. People may experience irritated eyes, coughing, headaches, breathing difficulty, and worsening symptoms from existing conditions. Even healthy people can be affected when smoke becomes dense enough or persists for several days. The safest response during unhealthy air quality periods is to reduce exposure. Keep windows and doors closed when possible, use indoor filtration, avoid strenuous outdoor activity, and follow local health guidance. A well-fitting respirator can offer more protection than a loose cloth mask during severe smoke, although official instructions should always take priority. As this Canadian fire season continues, the smoke problem will remain tied to the fire problem. Every new large blaze has the potential to create another long-range pollution event. And while officials continue monitoring Canada's forests, another environmental crisis on the opposite side of the planet is drawing attention for a very different reason. In one of the most remote and hostile places on Earth, scientists are watching an ice shelf that may soon lose the structural support, slowing the collapse of Thwaites Glacier. The glacier has been nicknamed the Doomsday Glacier because of its potential influence on global sea levels. Researchers say the remaining ice shelf at its front is breaking apart rapidly, and the process could accelerate the glacier's movement toward the ocean. Thwaites is enormous, roughly the size of Florida. Some sections are more than 500 feet thick, and the glacier stretches approximately 75 miles across at its widest point, making it one of the broadest glaciers on the planet. But its size is not the only reason scientists are concerned. Thwaites acts like a structural pillar supporting a much larger portion of the West Antarctic ice sheet. It helps slow the movement of ice behind it as that ice flows toward the ocean. If Thwaites were to disappear entirely, global sea levels could eventually rise by a little over 2 feet. But scientists are even more concerned about what could happen if its collapse destabilizes the larger ice sheet behind it. That surrounding ice contains enough water to raise global sea levels by roughly 10 feet if the entire system were eventually destabilized. This would not happen overnight, but even a fraction of that rise would reshape coastlines across the world. Cities such as Miami and London, low-lying regions of Bangladesh, and many Pacific Island communities are already vulnerable to smaller increases in sea level. A rise measured in feet rather than inches would push high tides, storm surges, and routine coastal flooding far beyond the limits of existing infrastructure. Governments would face difficult decisions about seawalls, relocation, drainage systems, insurance, and which communities could realistically remain protected. That is why a glacier in Antarctica has become a major focus for climate scientists and coastal planners. Since 2018, the International Thwaites Glacier Collaboration, a joint research effort involving American and British scientists, has carried out extensive fieldwork in the region. Researchers have deployed autonomous underwater vehicles, ice-breaking ships, GPS instruments anchored directly into the ice, and other equipment to track the glacier's movement. This sustained campaign has produced a detailed picture of the ice shelf, the ocean beneath it, and the bedrock on which the grounded glacier rests. A helpful way to understand Thwaites is to imagine a cork in a bottle. The glacier is the cork, while the ice behind it represents a much larger reservoir. Thwaites is not physically holding back all that ice like a rigid wall, but its resistance slows the outward flow. If that resistance weakens, the ice behind it may move more quickly toward the sea. For years, Thwaites has had a natural braking system, a floating extension called the Eastern Ice Shelf. This shelf sits where the glacier reaches the ocean and is partly supported by a raised ridge on the seafloor. The ridge helps anchor the shelf, while the floating ice pushes back against the grounded glacier behind it. That resistance is known as buttressing. The shelf does not stop the glacier completely, but it slows the speed at which ice flows into the ocean. If the shelf breaks apart, the grounded ice behind it loses part of that restraint. The difference between the glacier and the ice shelf is important. Thwaites begins on land, where its ice rests on bedrock and moves gradually downhill under the force of gravity. As it reaches the coast, part of the ice extends beyond the bedrock and begins floating on seawater. That floating section remains connected to the grounded ice behind it, allowing it to act as a brace. Remove the brace, and the ice behind it can accelerate. Scientists are now concerned that the remaining shelf is approaching that point. Robert Larter, a marine geophysicist with the British Antarctic Survey and coordinator of the United Kingdom side of the International Thwaites Glacier Collaboration, has warned that the ice shelf is likely to disintegrate before the end of this year. The precise manner of the collapse is uncertain, but researchers are increasingly confident that the breakup is coming. Satellite images show fractures developing in locations scientists had identified as especially vulnerable, including areas where the shelf is anchored against the underwater ridge and along the front where the shelf meets the glacier. Researchers have compared the pattern to a windshield developing a spreading network of cracks. Geophysicist Christian Wild of the University of Innsbruck has described large sections of the shelf breaking apart. Karen Alley of the University of Manitoba, who studied the region in 2019 and 2020, has said recent satellite images look dramatically different from what she observed only a few years earlier. The speed of that change is what has surprised many researchers. Movement on the western side of the shelf has approximately doubled over the past 8 months, while the shelf's flow rate nearly tripled between January 2020 and January of this year. It is now moving at slightly more than 2.0 meters per year, an extraordinary pace for a structure of this size. But the forces damaging the shelf are not coming only from above. Much of the attack is happening beneath the ice. Thwaites Glacier rests on bedrock that slopes downward as it extends inland. This shape allows relatively warm seawater to move beneath the glacier and reach areas far beyond the visible ice edge. The ocean water can melt the ice from below, even when the surface appears stable. Researchers using ice-breaking ships and an underwater robot called Icefin have confirmed that seawater is traveling more than 6 miles beneath the glacier. That water is actively accelerating melting at the base, particularly near the grounding zone where grounded ice begins to float. Scientific studies have shown that warm ocean water can rapidly thin Antarctic ice shelves from below. Recent research on Thwaites has also identified very high melt rates in vulnerable areas where channels intersect the grounding zone, especially above sloping bedrock that allows retreat to continue. Inland, the significance of the grounding zone cannot be overstated. It is the boundary between ice resting on bedrock and ice floating on the ocean. As melting causes the grounding line to retreat, more ice becomes exposed to seawater and begins floating. That can reduce the stabilizing contact with the bed below and allow the glacier to flow faster. The underwater robot IceFin was designed to examine precisely these hard-to-reach areas. Instead of relying only on measurements from the surface or satellite images from above, researchers can use the robot to inspect channels, cracks, and melting patterns beneath the ice. These observations help scientists understand why some parts of the glacier are changing faster than others. The same research traced Thwaites' retreat farther into the past than many people might expect. Scientists believe the glacier's decline may have begun as early as the 1940s, possibly after a powerful El Niño event altered ocean conditions along the Antarctic coast. That does not mean a single El Niño event caused the entire modern crisis. Natural climate variability can influence ocean temperatures and currents, but today's warming climate is changing the background conditions in which those events occur. Warmer oceans can make ice shelves more vulnerable, while rising air temperatures and shifting winds may create additional pressure. The current concern is not simply that Thwaites is losing ice. Antarctic glaciers naturally move and change. The problem is the combination of rapid flow, weakening buttressing, warm water beneath the ice, and a bedrock shape that may allow retreat to continue inland. If the eastern ice shelf disintegrates, the glacier may initially accelerate rather than collapse all at once. That distinction is important. The breakdown of the shelf is not expected to raise global sea levels by several feet immediately. Instead, it could remove a major break and increase the rate at which grounded ice flows into the ocean over the years and decades that follow. Scientists are still studying how quickly that acceleration could occur. Models contain uncertainty because the behavior of ice, water, bedrock, and fractures is extremely complex. But uncertainty about the exact timing does not mean the physical risk is insignificant. It means the range of possible outcomes remains wide. The same applies to the phrase Doomsday Glacier. The nickname is useful for communicating the potential importance of Thwaites, but it can also create confusion. Thwaites is not expected to suddenly vanish and flood the world this year. The immediate concern is that the ice shelf may lose its ability to slow the glacier, pushing the system toward faster long-term ice loss. That process connects directly to the future of coastal communities. Sea level rise does not need to reach 10 feet to cause serious damage. Even several inches can make coastal floods more frequent, increase the reach of storm surges, and worsen saltwater intrusion into freshwater systems. When higher sea levels combine with stronger storms or heavy rainfall, cities can experience flooding that once would have been considered rare. Coastal infrastructure is often designed around historical conditions. Roads, drainage systems, ports, seawalls, and buildings may not be able to cope with a steadily rising baseline. The effects can become especially severe during high tides or hurricanes, when water begins from a higher starting point. This is why scientists study Thwaites so closely. The glacier serves as an indicator of broader changes taking place in West Antarctica. Its behavior can reveal how warm ocean water interacts with ice shelves, how quickly grounding lines retreat, and whether current models are underestimating the speed of future ice loss. The research also shows the value of long-term observation. Without satellite records, underwater robots, GPS stations, and repeated expeditions, scientists would have far less information about how quickly the ice is changing. Each new measurement helps narrow the uncertainty, even if it cannot yet provide an exact date for collapse. And while Thwaites has become the most famous glacier in the story, it is not the only one at risk. Neighboring glaciers and ice shelves are connected through the broader structure of the West Antarctic ice sheet. The more Thwaites weakens, the more important it becomes to understand how the surrounding ice responds. The events unfolding in Canada's forests and beneath Antarctica's ice may appear unrelated, but they share a central message. Environmental risks can build quietly before suddenly affecting millions of people far beyond the original source. In Canada, a wildfire may begin in a remote forest, but its smoke can cross provincial borders and travel into the United States. A fire that starts hundreds or thousands of miles away can eventually affect the air breathed by people in Toronto, Boston, New York, or Washington. The immediate danger is not always where the flames are. It may be in the pollution carried by the wind. In Antarctica, the same pattern appears on a much longer timescale. Thwaites Glacier is far from most major population centers, but changes beneath its ice can influence sea levels worldwide. The collapse of an ice shelf would not create instant global flooding, but it could remove an important restraint and accelerate a process that reshapes coastlines over decades. The Canadian wildfire season is still evolving. Early numbers looked reassuring compared with the record-breaking seasons of 2023 and 2025, but that advantage has narrowed as fires spread across multiple provinces and territories. More than 800 fires have burned at the same time during the season. Smoke has crossed national borders, and federal forecasts continue to warn of heat and dryness through the summer. That means the rest of the season will depend heavily on weather. Rainfall could slow some fires, while heat waves and strong winds could cause others to expand rapidly. A province may experience temporary improvement while another faces a sudden emergency. Residents should therefore rely on current official fire maps, evacuation notices, and air quality readings rather than assuming that conditions from the previous day will remain unchanged. The same principle applies to Thwaites. Scientists know the ice shelf is fracturing and that warm seawater is melting the glacier from below. They know the shelf is moving faster and that its structural support is weakening, but they cannot yet identify the exact day when the remaining ice will disintegrate or precisely calculate how the glacier will respond afterward. What they can say is that the system is moving in a dangerous direction. The shelf's breakup could allow faster ice flow. Faster ice flow could increase ice loss into the ocean. Continued loss could contribute to higher sea levels and place additional pressure on vulnerable coastal regions. These are not problems that can be solved through one dramatic action after the crisis has already begun. Wildfire preparedness requires planning before evacuation orders are issued. Communities need emergency routes, shelters, communication systems, firefighting resources, and public health guidance in place before smoke fills the skies. Climate adaptation along coastlines requires the same long-term approach. Cities may need improved drainage, stronger flood defenses, updated building standards, restored wetlands, or carefully planned relocation from areas that become increasingly difficult to protect. Those decisions are expensive and politically difficult, but delaying them does not eliminate the underlying risk. The scientific evidence also shows why historical averages are becoming less reliable as a guide to future conditions. A fire season can begin slowly and still become severe later. A glacier can appear stable from the surface while warm seawater melts it underneath. The most important changes are sometimes hidden until they reach a threshold that becomes visible all at once. For Canada, the immediate priorities are clear: protect communities near active fires, support firefighters, monitor smoke, and reduce exposure to dangerous air. For Antarctica, the priority is sustained observation, because the ice system is too remote and complex to understand through occasional measurements alone. The broader lesson is not that every forecast points to catastrophe. It is that risk often grows through accumulation. Dry vegetation builds over weeks. Smoke spreads when winds align. Ocean water melts ice shelf foundations over years. Small changes can compound until a system becomes much more difficult to manage. Canada's fires are burning now, and the worst of the season may still lie ahead if hot, dry weather persists. Thwaites Glacier is also changing now, and the collapse of its remaining ice shelf could mark another step toward faster long-term ice loss. In both cases, Scientists are not offering certainty about the exact timing of the next major development. They are identifying warning signs and showing where preparation matters most. The flames in Canada and the fractures in Antarctica are separated by thousands of miles, but they are connected by the same need for clear information, sustained monitoring, and serious planning. These crises are not distant stories anymore. One is already affecting the air people breathe across a continent. The other is altering the future of coastlines around the world. And if the evidence from both systems is pointing in the same direction, the most responsible response is not panic. It is preparation before the next escalation arrives.